Johnny coming?
No idea.
Okay. So there is a homework that's due tomorrow.
Mm.
All will be due next week. Midterm is prior from Was there any progress on when we are having the exam? I think since I didn't hear anything from Rob about this, we did discuss it. So let's stick to September 24th, Friday during the class.
Oh,
Again, 1 week before is, you can still change, but let's stick to it. So we want to switch gears and start a new topic. Maybe you've come across this before. We want to do complex numbers. Right. And more than complex number, complex analysis. Basically, we want to not just introduce complex numbers, we want to there is a property of the complex plane that leads to its derivative having very special properties. So we are first define a derivative on a complex plane, and unlike a two-dimensional plane, this will have very special properties, and that leads to it being very useful for our, or it has a lot of applications. So to introduce the idea of complex number to begin with, so let's start. We have we'll define three concepts. So one is, let's say, countable set. Just broadly, I'm just motivating the whole idea. I won't be going into the details. It's just to give you a thought, a collection of thoughts, if you want. There is the idea of ordered set. And there is the idea of a dense set. Just an idea, I'm not going to make it very precise like that you will see in some mathematics course. So what is a countable set?
integers.
Integers are countable. Yeah, that's a interesting examples because it also is infinite.
Mm-hmm.
Right?
Oh, yeah.
Even though it is infinite, you still say it is countable, right? So, so maybe I should also in the beginning say finite versus infinite, infinite. So there's a distinction between that, and finite infinite is very easy. Something that has infinite numbers or infinite set, and something that has finite, like 6 people in it in the set, that's okay. Countable now, if it is finite, it is very reasonable. We know how to it's fine. If it is finite, by definition, it is countable. But now if it is infinite, then we have to distinguish between them. For example, we could ask, does the natural numbers have more numbers or integers have more numbers? Right. So that's a question that comes up. So let me define some sets here. So there is natural numbers, right? That's what it's called. Natural numbers. That's 1, 2, 3, 4, and so on. And then there is whole numbers. This is basically 0, 1, 2, 3, and so on. That is integers. And this will be minus 2, minus 1, 0, 1, 2, and so on. And what next after integers? What are the other sets of numbers you've seen? Anything else you can think of? Rational numbers? And that involves any number that can be written in the form m over n. And where m and n belong to natural numbers, actually integers, right? Okay, that's clear. What else? What is the other number system you've seen?
Irrational.
Irrational, right? Numbers, and what's an irrational number?
Pi.
Pi, example is pi. Yes, that's correct. Definition by any chance?
Non-repeated. Non-repeated integers like
Non-repetitive.
repetition.
Correct. So the pattern doesn't repeat at all. So for example, when we say 1 over 3 is 0.333, like there's a pattern which I can predict. So I can create a formula for predicting the 278 decimal. In this case, it is trivial. Even if it is, let's say 0.3012, 0.123, that's a rational number because its pattern can be predicted, and this can be written in. And anything that repeats itself, you can write it as m over n. Okay. So that leads to an extra credit problem, right? Create a formula for such. Like given a 3-digit repetitive number, given a 3-digit, or 3-digit means it repeats after 3 digits, give a formula for what's the algorithm you will create to come up with m over n. So that is the question. Okay, so that's just an exercise. So rational is, as you said, the pattern doesn't repeat itself. Pi is, that's why pi, we don't know the numbers, right? We have to every other day we happen to create one more number. There's a lot of interest in that, but in general, it's, you cannot have a formula for it. So that's irrational number, and you want to think of this in terms of these 4 properties. That's an irrational number, and irrational and rational is real. And let's for a moment stop here. We'll come back to this. Okay. So let's go back and ask: is natural numbers finite or infinite? It's infinite, right? That's by like the moment we read those 3 dashes. That means that this is infinite. This is infinite. This is infinite. Everything we have is having an infinite. And so they're all infinite sets. Is it countable? So natural numbers, is it countable? So you actually said that that was a good one. Yes, that is countable. That's perfectly fine. Then we have to think about what we mean by countable. So we try to define that. To motivate that, we ask the question, is whole number countable or not? In one way you would say, yeah, probably yes. But then maybe, again, I repeat, which one has more number of elements in it? So they're countable. But which of this has whole numbers versus natural numbers? Which one has more number of elements in it? Whole number, right? I mean, one would think naively that yes, that should be the case. But actually, no, right? So the I mean, again, it depends on the definition. If you say that, okay, this element is this element is this, remove all that and I'm left out with one, so that should be more, right? That's one way of arguing. But here is how we will define how whether something is countable or more than countable. Can we associate this with this? So the idea is you will associate 0 with 1. You're counting, right? I'm saying I'm going to put a label, like if I want to count the number of bisons in a farm, right? Then you would say that, okay, this is 1, that's 2, that's 3, and I keep going. Right? If it's infinite, I'll keep going, otherwise I'll end somewhere. So this is my, it's going to be the algorithm for countable. So any number, this could be anything, it happens to be numbers again. This is 2, this is the second element in the set, that's the third element in the set, and that's the fourth element, and that's an algorithm. And I keep doing that forever, give me forever, and I'll keep doing that forever. And I say that that's an algorithm, that it's n minus 1. In that sense, there's a one-to-one mapping from here to there. Since the last element doesn't exist, it is okay to do this definition. Is that clear? If the last element existed, if it was finite set, you couldn't have argued this, because then you would be left out with 1. But just because it is infinite, its property has changed a little, and you can say that these two are the same number of sets. Okay. With that in mind, now let me ask: is this integers have more number of elements, or whole numbers have more number of elements?
Integers, they also have infinite.
They also have infinite, right? But just because it's infinite doesn't mean that you need to come up with an algorithm where you can associate one-to-one with this. Okay?
Integer.
With integers and whole numbers, one-to-one mapping. Okay. So your procedure would be: I start with 1 with 0, 2 with this, 3 with this side, right? 4 with this side, 5 with this side. I keep doing that forever, and I'll reach forever. Like I'll be able to count one-to-one mapping, and that'll be a unique mapping there. Is that clear? That like this will be a 2 raised to n on the right side, you'll get 2 raised to n. This will be 2 raised to n plus 1. That n is equal to 0, 1, 2, 3, and you will always be able to get the nth number. There's a formula for that, and you can get that. Is that clear? In that sense, this also has exactly the same number of elements as the natural numbers. Is that reasonable? Right? So, is natural numbers countable? Ordered means, are they, can you say one is less than the other? So here there is an order, right? We always, by construction, our numbers on a number line has an ordered pattern. What about rational numbers? Oh, by the way, dense set. What is dense? Pick 2 numbers. You should be able to define a third number in between. Give any 2 numbers, you should be able to define a third number inside. So give me 0 and 1. Can I define another number in between? No. Right? 0 and 1, there's a boundary there. Right? After 0 comes 1. But it is ordered. So now the first dense set we see is rational. Okay, so let's see these properties again. Rational number, is it finite or infinite? Is infinite? Is it countable?
Yes.
Right? Now, if it is countable, remember you have to have a one-to-one mapping from here to there.
Decimal.
Right? So now we are decimals. So can you do a countable? And but before that, let us say I'll postpone that a minute. Is it ordered or not? Yes, rational numbers are on a number line, right? So this is ordered. Or is it dense or not? Dense means give any two rational numbers. Can I create a third one in between? Like, for example, if you have 0 and 1, give me any number, even how far ever you close to 0, you give me a rational number, I'll create another one, I'll just average it, right? 0 plus that rational number and divide by 2, it's a new rational number. So it's dense in that sense, like you can only limit approach the 0. There is no closest number to 0, you can only approach it. In that sense, it's dense. That's the idea of it. In calculus, we say infinitesimally code. Correct? Is that clear? So it is dense, and dense seems to suggest that this must really have a lot more numbers than this. Right? Again, intuitively speaking, but our definition has nothing to do with the intuition of how many are there in a density. Well, our definition is that can you form a one-to-one mapping between these? Right? And the answer is yes, you can form. So here is the you can do the following. So first of all, we should be able to get a pattern for rational number, right? So what you can do is have m here and n there, and this is 1, 2, 3, 4, and so on. And do this negative also. Every point in this way of creation is m over n, right? So that's a rational set. You can argue that, oh, what if it is like usually rational numbers has to be simplified, but that's okay. So you can remove some of them, but otherwise you can say that whenever it's the same, you can associate it back to the other one. And keep going, except that there is n equal to 0 is not allowed. Right? So this n equal to 0, this line is not allowed. N equal to 0 is not allowed. Otherwise, every point in here represents a rational number. We want to make a map from here to natural numbers. So what you would do is, let's at least do one quadrant. You can start from here, right? And go there. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And I can keep going. Well, then you would say, oh, I missed this quadrant completely. If you want, when I am here, you can go this way, right? So this way. Oh, this was not there, right? So let's say after this point, you come so this one, this one, this one, this one. You can go this way. So there is a pattern you can create, and I can keep going forever. And since infinite number is not there, I'll keep going it. I can get the nth number, and that's okay. So it's finite actually. So you can actually place it on a spiral kind of situation. Is that clear? Roughly motivating what that this is actually having the same number of elements of this. So is rational number countable? Yes, it is countable, and the moment it is countable, that means it is another one-to-one mapping. Is it ordered? It is ordered because it's on a line. And is it dense? It is dense. Right? So that's so now comes irrational numbers. And is irrational number finite or infinite? It is infinite because you can keep going forever and still get it. Is it countable or not? It is not countable for the first time, and that's the whole idea that we don't have a pattern. Right? Since we don't have a pattern, the whole idea is that we cannot map from one to the other. That is slightly more complicated than that. So just to convince you, I typically like to give the argument of Cantor. So this was first a very simple argument, but a very powerful argument, and it came only in the 1870s or something. I think somewhere in 1870 or maybe 1800s. I'm not sure. Okay, so here is the argument. So the idea is to prove that the irrational number is countable. So we want to have we want to show that it is not possible to have a one-to-one mapping. And whenever you have one, you want to prove that it is not possible to have a one-to-one mapping, you find a contradiction, right? At least there exists one number which you can generate, which is not having such a pattern. So the idea is that, again, we want to have this ordered set. So you list all the irrational numbers in an order, right? So if it is countable, we are saying that is 1, 2, 3, 4, and so on. And every irrational number, there is a one-to-one mapping. So I randomly put some numbers, so 5.621 and so on. That's an irrational number, so it can keep going. Right. So this is, let's say, 19.12375. Again, it has to keep going. Right? And let's say this is 7.5621. Again, keeps going. So since it's an irrational number, there is no pattern in this. But I'm saying that to disprove the theorem, I'm saying that there exists a one-to-one mapping between these. Correct. That means I can associate this with 1, this with 2, this with 3, and so on. And we are saying that all the irrational numbers can be listed like this. That's what we mean by it is countable or not. So to disprove that, so what Cantor said is that, okay, here is a number I will create. So he said, give me any list like this, and he will give an irrational number which does not belong to the list. Right? And then he has proved it. Right? So he said, okay, so his simple algorithm is take the first number. So let's say he starts with 0, okay, and he, after the decimal, take the first decimal and 6, right? Just add one number to that, so it's 7. It's 6 only. Anything other than 6, okay, put that in here. Second number, go to the second decimal. This is 2. Okay, put anything other than 2. So let's say the next number, that's 3. Go to the next number, that's 2. So make it 3 again. And you keep doing this forever. Right? You keep doing this for the whole list, and you have created a new number. Now, Cantor's argument is that this does not belong to this set. Why? It is not the first number because the first decimal doesn't match. It's not the second number because the second decimal doesn't match. It is not the third because the third decimal doesn't match, and so on. So this number doesn't exist in this, but this is a rational number, right? Because if there is no pattern in any of these numbers, then there cannot be any pattern in there either. So that's a simple, again, try to simple idea, but I think a very powerful proof in there. So irrational number is ordered in the sense that in given any, you can say is less or more, and divided by right double time 2 times. And it is dense also. The irrational number is dense. Is it countable? Not countable. Is it ordered? It is ordered. And real numbers are rational plus irrational. Right? Rational plus irrational. And there was clear motivation for why did we do all this. We started with addition. Addition is confined to natural numbers. If you're subtracting 2 minus 2, suddenly there's a 0. If you don't have that, you define it. You subtract 2 minus 3, you wanted whole numbers. You started multiplying or dividing, let's say you started having rational numbers. and irrational numbers comes in when you're starting square roots, right? So more operations you define, and there was a natural need for more number of steps. What after real numbers? And that's what we are going to deal with here. We will deal with complex numbers. And then comes the idea of, are you familiar with complex numbers, by the way? Have you studied complex numbers somewhere else? In any other subject? Mathematics, most probably, or
IX was the like
that's correct. That's exactly the complex numbers. I mean, some introductory level, very elementary level complex numbers. Like it is basically having a square root. So I don't have to repeat those things. So we'll define it more clearly in a few minutes. But the point is, can I speak about complex numbers? Right. So a rough idea is that. So complex numbers. Again, if I ask, is it infinite or finite? How many numbers are there? It is typically x plus iy, right? With I having some significance. But this is a complex plane, right? That's x, that's a y. So that's a two-dimensional plane. If a line itself is infinite number of elements, then this is a double infinite in a sense. But again, what does it mean to say double infinite? I mean, there is no such thing as double infinite. There are properties related to infinity, but it is R2 space. Is it countable? Real number is not countable because it has irrational numbers, so it is not countable. Is it ordered? No, really. For example, if you're on a circle, right? Like between this number and this number, which one is bigger? Magnitude-wise, you can say, in this case, both are equal. There is no ordering in complex numbers, right? There is, to a certain extent, ordering in the sense that when you have vectors, you can say that is the magnitude of this the same or not. But once the magnitude is the same, it could be anywhere on the circle. So in that sense, there is no ordering. Is that clear? Right. So there is no ordering in complex numbers in the strict sense that you cannot say A is less than B or not. Right. If you have vectors, for example, what do you mean by A is less than B? Or what I mean to say is that ordering should be, if A is less than B and B is less than C, can you say that A is less than C? That will be ordering, right? If A is less than B and B is less than C, then does it imply that A is less than C? That would mean that ordering, and that's not necessary, right? You can always construct three vectors and have A less than B, but B less than C, but A need not be less than C. Give an example. In vectors. Oh, it's not a good question because you're saying that this less than itself is not very clear, right? Only when you write magnitude, it's clear. So the question itself is not relevant because it doesn't have a ordering is not there at all. So this question is not relevant. Okay. So doesn't have order, but it's still dense, right? Complex numbers is dense. Take any two complex numbers. In fact, now on a real line, you would say that give me any two and you can construct in between. Now you're saying that on a complex plane, give me any two complex plane and I can get a whole plane of them, right? Or numbers on a whole region which are close to 2 points. Right? So in that sense, complex numbers associates with these numbers. Just for completion, can you keep going forward? Is that more than complex numbers, real numbers, complex numbers? What is it? Anything you come across? It's something more than complex numbers. There are, and just for information, so this is quaternions. Have you come across this word? Right, quaternions. the idea is, okay, and again, so this is x plus iy, right? So what you have done actually is that you've introduced one special symbol, I, and used that to create an algebra of two-dimensional plane. Right? It's a new algebra, but you first say that how I works. Right? I times x is how much, I times y is how much, and I times I is how much. Right? So create some rules. But then immediately the question comes, what about this? There is an I1 times y plus I2 times z. Is that also possible? Okay, is that clear? So this time this was a two-dimensional plane. You set a three-dimensional plane or three-dimensional space. And now I have to specify the operations for I1 times I1, what is I2 times I2, and so on. And it turns out, and this was the idea with which Hamilton struggled a lot. But what he realized is that you cannot do this for two-dimensional, but if you add one more, that's possible. So that's your quaternion. You put in three i's, and the best way to see this is a quaternion is, don't think of, since we do physics and we do a lot of quantum mechanics, this is nice to see this as sigma. This is x0, sigma 1, x1 plus sigma 2, x2 plus sigma 3, x3. Where sigma 1, sigma 2, sigma 3 is a spin of an electron, the components of the spin of an electron, which are called polymatrices. Are you familiar with that? Polymatrices? Okay, again, quiz. So quiz polymatrices. Let's read up polymatrices. And x1, x2, x3 are numbers. X0 are real numbers. Okay. So that's a quaternion just for listing. And there is one more in this list, and that's octonions. And this is the same idea, but instead of 4, you have 8 of them. So octonions is x0 plus, let's say, tau 1, x1 plus tau 7. I think so, yeah. Right, there's 7, right? Not including this is this. And there are properties of tau 1 to tau 7. Okay. And it turns out that you cannot, so the immediately the question goes, okay, what next, right? Can there be a 16 or 20, 32, or for that matter, any number that can generate an algebra? Algebra means that you can define a multiplication, you can define a division, you can define all these operations that are useful, and they should be contained inside the set itself. And it turns out that as of now, no one has discovered anything beyond, and as far as I know, there is a proof that it stops here. Right? There's no more, at least in this sequence of numbers. But we will concentrate on this. We want to ask what is complex numbers and so as we roughly I pointed out, complex numbers. So we first define a symbol, which is I, which is going to be square root of -1, which is before complex numbers, we cannot do it, right? What is square root of minus? We don't know, right? That is no. It's not a real number for sure. And so you define that to be equal to a symbol. And then you define some properties associated with it. And you say that what is I squared? So that is I times I times I or I squared, right? I squared is -1. And what is I cubed? So it will be minus I. And I raised to 4 will be equal to 1. And once you reach 1, then you can generate all the others. So that's going to be our rule book, if you want. Based on this, we will construct a complex number Z as consisting of two numbers x plus I times y. So the moment you write this complex numbers, so there is a number and a symbol, right? So we have to create all rules related to addition, multiplication. So how does I work with the y? Is I times y the same as y times I? Right? Is I times x the same as x times I? And all those rules you have to create. And that's why I will assume that you have had a course on complex numbers and we know how to add and multiply numbers. So 2 times I is the same as, the 2 times I is the same as I times 2. These kind of statements, I won't list things down, but in principle, when you're doing a real starting from the scratch, you really specify what are the rules of how this I works with any other number. If it's 3 or 276 times I, how does it work? So we specify those things, and this is going to be in general what a complex number is, and x and y is going to be real. X, y is real. It belongs to real, that means it's real, and z is going to be complex number. And this is a complex number, typically it's given there. How do you visualize this? Best is to see this as a two-dimensional plane, right? X and y, since I is a symbol, so you want to, every combination of x and y is a complex number. You want to visualize that, you take a grid, right? That's the best way of doing. That's what you do in a two-dimensional plane also. And now we want to define operations on it. First is addition and subtraction, straightforward. So let's say this is z1 is equal to x1 plus I times y1, and z2 is equal to x2 plus I times y2. So addition will be equal to, so z1 plus z2 will be equal to x1 plus x2. And now, so let's write this in the following form. So you're saying x1 plus iy1, right? That's what you'd say, plus x2 plus I times y2. And now the point is, this is a special element because there's a, I don't know how to add this x and y, but x1 and x2 I know how to add, right? So I keep that together, x1 and x2. And next one is I times y1 plus I times y2. And now we have to construct rules of how do you add this quantity. And here we will say that it is possible to factor out I. Right? That's again listing the rules of how complex numbers work with the real numbers. So this is equal to x1 plus x2 plus I times y1 plus y2. So this is, so the moment you introduce those rules, addition has been defined. So if you want, this is a definition of addition of complex numbers. Subtraction goes the same way. This is minus, that's minus, that's minus, and this is minus. And this is straightforward. Okay. And if you compare this with vector addition. So if you have A plus B, A is AX, let's say A1 I hat plus A2 J hat. And if you have B, what is A plus B? That's exactly A1 plus B1. I have and A2 plus B2 in the J hat. If you were to have a complex plane with two complex numbers and you add them, they will pretty much look like your A plus B in a vector space. There's an addition of two vectors. Addition and subtraction of two vectors has a one-to-one correspondence between addition and subtraction in complex plane. That should be, again, elementary. This is, we can subtract also and get exactly the same thing. All this is fine. So it seems like complex numbers has a lot of properties associated with vectors in 2 dimensions. But now we say, what about multiplication and division? That's where it's getting different. And for that purpose, let's define what is called a conjugate of a complex conjugate. So let's define the idea of complex conjugate. So complex conjugate will be if you have Z is equal to X plus IY. That's a complex, general complex number. A complex conjugate will be represented by Z star. That's a complex conjugate. It's complex conjugate of Z. That's Z star. Sometimes in mathematics you say Z bar, right? Different textbooks tries to use different symbol. Actually, in physics, in quantum mechanics, we will use Z bar, right? Complex conjugate is typically as a wave function as a bar. We use here we will use star to represent complex conjugation. Okay. So this is equal to just if this is a complex number, then it is X minus IY. So you replace I with minus I. Wherever you see I, put in minus I. And where, how does it look like if you have a complex number Z, which is, that's your Z. And so that's your Y, and that's your X. I'm flipping that. Complex number will be here. That's Z star. Okay. Right. So it's just if you have a vector, we're saying that it is a minus B. And that's a useful concept when it comes to multiplication of a number. But before that, then we can define the moment you have this, it's good to ask what is addition and subtraction, right? Addition and subtraction is just 2x. So if you add, it is 2x and it is purely real. And if you subtract, it is purely imaginary. Right? That's one property you can define. Okay, so that's good. So now with all this, let's do the multiplications. So multiplication will be defined as, let's see how it will be. So this is Z1 times Z2. So Z1 is X1 plus IY1. Z2 is equal to X2 plus IY2. And Z1 times Z2 defined as, let's first put in all the numbers right away. Right? It's X1 plus IY1 plus, or not plus, multiplication. Right? So this is X2 plus IY2. Now again, we have to generate rules for how do we do the multiplication. We will have the same distribution law. So X1 plus times X2, same distribution law. X1 times X2. X1, let me be careful here. So just to show you what are the new properties we are introducing. We only know how to multiply two numbers, right? Or now there is a new property here, I. So it's not very obvious to me. Can I move the I on this side? It's not there. So this is I times Y1 X2 plus I times Y1 times I times Y2. Again, principle, that's the kind of operations we are dealing with. Now we say that any real number and the symbol I, they commute in the sense I can move I times X1 is the same as X1 times I. Give me a quantity that does not satisfy that. A times B is not the same as B times A. A times B is not the same as B times A.
Vectors. You can vector A.
Vectors. A dot B is, you mean scalar product? A dot B is the same as B dot A, but maybe like if I tell you that A times B is not equal to B times A, what is A? Or what is A and B? So that means AB minus BA is not equal to 0. Right? 2 times 3 minus 3 times 2 is 0, right? And where do you so think of quantum mechanics, x times p minus p times x, what is that equal to? IH bar, right? That's uncertainty relation, Heisenberg uncertainty relation, right? So what is x and p in quantum mechanics?
Operators.
Operators, right? So operators don't satisfy. Or what else? Matrices. Right. So if whenever you say, oh, AB is not equal to BA, matrices are examples. Operators are examples, like differential operators, like angular momentum, differential operators. That's example of that. And that's the two that immediately comes to mind. Or cross product, right? You said vector product, but then I confused you with the scalar product. Vector product, if you say A cross B is not the same as B cross A, right? So the minus sign that comes in. So you have come across things that do not satisfy that. So it's not very obvious whether I times x1 is the same as x1 times I1, but you define that it is the same. So they do commute. I times x1 commute. So I can move. I is already moved. And here, after I move the I, then there's an I square. Right? And I square is minus 1. We defined that. So there's a lot of properties that went into this, which I'm not specifying here, but you should build on all that. You have to list down all the properties that, oh, do they commute, do they do not commute, what happens when it multiplies with a number, what happens when it multiplies with a 0, anything special. So this is equal to x1 times x2, and there's an I square, so this is minus y1 times y2. Now it's real, right? These two are real numbers, so that's the real quantity. You moved I, so I can be factored out. Like all that are even I factoring out, that's not very obvious. That is it allowed to factor out? So Is that the same as vector multiplication? Right, to begin with, what do you mean by vector multiplication? As I said, there are two vector multiplications, right? It is not even clear what is there. Like A dotted with B has something, A cross B has something. But incidentally, there is a connection between the multiplication, but not a straightforward connection at all. So let's say, so to see that connection, let's say Z1, let's do Z1 multiplied with Z2, Z1 star multiplied with Z2. Z1 star means it's complex conjugate, so there's a minus sign I've introduced in here. And if I follow that step, then this becomes x1, x2 plus y1, y2. And the cross terms is equal to plus I times x1, y2 minus y1, x2. Is that clear? Acceptable? I jumped steps, but that should be clear. But now let's say these are vectors, right? This is one vector, that's two second vector. Z1 is visible. So Z1 is equal to x1 I hat plus y1 j hat. And Z2 is equal to x2 I hat plus y2 j hat. Like I'm again writing this as with the same variable, but this is understood that Z1 and Z2 are vectors now, correct? What is Z1 dotted with Z2? That's x1, x2 plus y1, y2. That's exactly this. So the real part of complex numbers, if visualized as the corresponding real numbers, is actually Z1 dotted with Z2. Is that clear? I mean, this is slightly misleading because this is not the same Z1 there, right? This is the magnitude of the corresponding thing that happens in the space of vectors plus x1 y2 minus y1 x2. Think of cross product. Now Z1 crossed with Z2. First of all, Z1 crossed with Z2, these two are in a plane. This will be in the K space, right? This is K space. And its cross product will be x1, y2 minus x2, y1. So that's exactly this. So I would say plus I times, right? Remove the K hat, and it is Z1 crossed with Z2. But I want to remove that K hat because I want a scalar, right? So I will dot it with K hat. So this is not I hat, that's I. Dotted with K hat. Is that clear? So that's just to give you a picture of, yeah, there is a connection. So it's kind of a nice connection. This is scalar product, that's a cross product. But now they sit as the imaginary and the real part of the complex product. Okay. Okay, so that's multiplication. So it's as we noticed, multiplication of complex numbers cannot be associated with there's no direct association between multiplication and vectors. Right? To get taught with multiplication and vectors is not unique. There are two such products. Okay, so that's multiplication, and then we come to division. Right? So what happens to division? And that's where that complex conjugate really helps. Any questions or comments on that? Okay, so division, involves a number in the denominator. So let's begin with division. Let's begin by asking, what do we mean by 1 over Z1? Because once I can associate this, what this means, then I can define division in general. Actually, before that, let me go back to multiplication and get something. What is the magnitude of a complex number? Since we define multiplication, it is good to ask what is Z1 star times Z1. As Z1 is a complex number, we defined what is Z1 star times Z2, two different complex numbers. What if it's the same? Then the imaginary part goes away, right? If it's the same number, then it is x squared minus y squared. So this is real to begin with. So this is x1 squared plus y1 squared. So imaginary part goes away. And this we will say is the magnitude of a complex number. So we will define what is called a magnitude of a complex number. Will be Z star times Z and then square the magnitude. So magnitude square will be Z star times Z. Since this is the sum of a square of two real numbers, this is always greater than 0. It can be 0 if x and y is 0, greater than or equal to 0. Right. And since it is always greater than or equal to 0, you say that, okay, this is going to be defined as the magnitude or absolute value of the complex number. Right. So this is also called the absolute value. With that, now let's go to division. We have addition, subtraction, and the magnitude of a complex number. And you say that, okay, what is 1 over Z1? Let's define that first, 1 over Z, let's say. And that is, if I were to explicitly write it, it is 1 over x plus I times y. Let's pretend we are actually doing normal complex normal numbers. So you would say this is the same as 1 over Z, but normal numbers satisfy. I can multiply a Z star here and a Z star here. If I multiply on the numerator and denominator, that should be the same. But in the denominator, the multiplication has a meaning, right? Z times Z star. That's your x squared plus y squared. So what is this? This is x plus iy. And the denominator is real, and we know how to work with real numbers. Oh, x minus, that's x minus iy.
Down also minus.
What is minus?
X square minus y square or
No, z times z star is x squared plus y squared, right?
no, minus.
Correct. Z times z star will be x squared plus y squared. And now this is very nice because this is clean, right? We know how to do these operations. Minus of I times y over x squared plus y squared. Right. Get this number x divided by x squared plus y squared. I know how to do this division. This is a usual division. This is a usual division, and we are not getting anything new. That's your definition of division. So basically, the idea is whenever you want to define a division, you will multiply a complex conjugate. So it is z star over the magnitude of z. With that, you can actually define any arbitrary division now. So any arbitrary division would be z1 divided by z2, right? Will be equal to multiply Z2 star on both sides. So this is Z1 times Z2 star. And this is Z2 times Z2 star. And that's the same as Z1 Z2 star divided by magnitude square. So it's basically you convert the division into a multiplication problem by multiplying a complex conjugate on this. Okay, what else? Yeah. So that's all good. So now we know we have defined addition, subtraction, multiplication, and division. And the main idea, of course, was that we can actually now do square root of 16, right? So square root of 16 is how much? This is square root of -1 times square root of 16. Right? And this is I, that's 4. That's 4 times I. Right. So that was the whole motivation of introducing complex numbers, that this works. And it was, so this seems very artificial, right? You say that, okay, if you want to define a square root of -16, like that's why you did this. But in the historical sense, that's not how it went. It was not because they wanted to define square root of -16. Of course, this is where the context came in. The main context was how to find this cube root of a, or how do you find the roots of a cubic equation? That is where it showed up, and it is sort of interesting. So let me try to say that. This. Okay, so suppose so this is roots of a cubic equation, like quadratic equation, right? Quadratic equation. Let's begin with quadratic equation. And when we say roots of a quadratic equation, what we mean is that, okay, give me this. That's a general quadratic equation. And what is x now? If I tell you that this is equal to 0, what is x? Yes? No? Yes. Yeah, what's that?
Minus b plus minus.
Minus b? Is that what it is?
Yeah, minus b plus minus.
Minus b plus or minus
Under b square minus 2.
5 to 8. Right? That means to say that give me a, b, and c, you can find x always. That you're given a formula for that. That exists for every quadratic equation can be solved. Right? It is possible that you might not get a negative root of this. Right? And if you're not familiar with complex numbers, then you say that, then that's not a real number. It doesn't exist. But then if you know complex numbers, it always comes with 2 solutions. Right? Always there are 2 solutions, might be complex. And if they're complex, they always are complex conjugates of each other. Is that clear? The same thing, now you can ask, what a cubic equation? And let's say it is ax cubed plus bx squared, cx plus d is equal to 0, right? What's the solution for a cubic equation? That's not a very common thing we study, but let's go back to this quadratic equation. This always looks like this, right? This is always here or here, right? Either up, facing upward. That's a parallel. How will a cubic equation look like? Like it will go up and down, actually. So it will go like this. It will, for very large x, like let's say x is very large, that means this is x, right? For very large x, this will dominate. Forget about x. Eventually, this will dominate. And x cubed is very large. So For a very small x, this will dominate, so it's minus of that, so that will go down. So that's how you get these two. And somewhere in between, there will be this, go up and down. And what you can do is, there is this point here, there's a symmetric point in there. It will be symmetric about this point in the sense, if you go this side so much distance, and this side it will be the same pattern. So this curve always has that symmetry. Once you learn that, you actually move that center to this. At this center, if you move it, what will this equation become? If you move the center of the parabola to at the origin, what will that equation look like?
X squared.
Just x squared, right? This linear term is gone. This constant also is gone. So it's just x squared with some constant in front, right? Same thing, if you do it here, it won't be just x cubed. This can be converted into x cubed plus px plus q equal to 0, just by moving that origin. Okay. So any cubic equation, just by moving that origin, can be done into this. And in 1500, once they realized that this was possible, then there is this is called the Cardano formula. Italian Cardano. I don't know, Cardano. I think he gave. I'm sure I'm not pronouncing it correct. Cardano formula. And there is a solution for the cubic equation, which is the following. And it is given as minus q over 2 plus p over 2 is p square of 4, q square of 4. Is it p or q? Q. It is q over 2 the whole square plus p over 3 the whole cube. Q plus 4 cube. Right? And then you take the square root of this, and then you take cube root. And then you add that next one. So now here is what was very baffling to in the 1500s, that or what Cardano found, or what made them very curious in 1500s is that if you were to have the following equation, let's have an example. Right? So let's say x cubed, this was minus 15x, and I think this as 4 is equal to 0. Just by playing around with it, they knew that 4 is a solution, like 4 into 4, 16 into 4 is 64, 15 into 4 is 60, 4, 64. Just by guessing it, you know that x equal to 4 is a solution. It's a cube root, so it will have more solutions. So in fact, there is 2 more. So it is minus 2 plus root 3. And in fact, minus 2 minus root 3. That's your 3 solution. Again, you can just substitute this in here and figure that out. Okay. But, and they also and once Cardano, like this is about 1540. They also realize that if they do this, use this formula, they will get this number. Now, here is the interesting part. If you put this 15 and 4 in this, here it says that x is equal to This is q is 4, so that's 2, right? So just 2, and if you do this, this is plus 11i. Well, that's cube root. And this is so the idea was that the right hand side is not really a real number, right? It doesn't seem like it's a real number. The solution, oh, sorry, the solution here, right? So this is a real number. So here was a explicit example as to, oh, what is happening here? Left side is a real number, but right side is not built out of real numbers. Right? So then the immediate question comes, okay, how do I define this, right? So what is a cube root of a complex number? So we have to ask about what is cube root, what is fourth root, and so on. There, it's a cyclic problem in the sense we started by asking what's a cube root of a number, but now this is real, right? See, notice we're not really here. If I had asked this, what is square root of minus 16, then the problem is what is square root of minus, then I'm really asking what is a cube root of a negative number. That's not the issue here. The solution here is real. You're not needing to go to complex numbers. These are real numbers. We know there are real solutions. But the answer cannot answer in a certain using a certain formula cannot be written as a real number. It has to be written in this form, and then you make your operations. And if you play the game of this I, which is square root of minus 1, then you get this to be 4. Right? You do some new mathematics, if you want, in 1550, complex numbers was not acceptable. Right? That's not known. If you play around with it, and if you, like Cardano gave some rules, you can get a number which is real. Otherwise, you cannot get this. Like you would say that, oh, how do you get that 4 other than playing around with it? This should be compared with what we are struggling with these days. These days, we know we play with infinities, right? And we add and subtract infinities. Often we don't know what, it's not acceptable, right? I mean, they don't obey the rules, the standard rules of addition and subtraction of numbers. But often we know that it is giving the right answer. Right? Similarly, for 400, these days you can play around with complex numbers and no one will object you. In fact, if you don't, they will object you if you don't know complex numbers. But those days it was not acceptable. In fact, it went along all the way to 1830s or 1805, I would say, 1805. Until 1805, and why did that happen? That was Argon. Because people did not have a visual picture of a complex number. What Argon did is that he showed that a complex number, complex multiplication actually can be visualized as a polar diagram with an angle theta, which has a face of a complex number and a magnitude of a complex number, pretty much like a polar vector, if you want. And then there was a visual representation of the whole thing, and that worked out. In fact, Argon came after Euler, and Euler, remember, is one of the most prolific mathematicians. He almost did everything. Even he struggled with complex numbers, right? Because Argon came after him. So Euler made mistakes with dealing with complex numbers, like this is also a good example. Like, what is square root of minus 6 times square root of minus 6? Right? These are now we're talking about multiplication of two complex numbers, and just I'll take 1 minute. I know you guys have another class. If you multiply two complex numbers, there are two ways of doing this, and that was the confusion. Let's say two ways, right? So I'll multiply this. One way is to first do the square, right? This is one number multiplied with the wrong number, the square root goes away. This is minus 6 times minus 6, and that is 36. That's okay. But now let's do the opposite. Square root of x times y is also square root of x times y. So that's the same as square root of minus 6 times minus 6. That's square root of 36. What did I do? Did I mess up? No, what I wanted to do was,
Imaginary number.
yeah, this one, I wanted to do the opposite way. This is the same as square root of minus 1 times 6, square root of minus 1 times 6, right? And that's minus 36, right? And this one, this way of doing it, if I take them as a square, then that is a 36. So
6 is also in root.
what is happening here?
That, what
Yeah,
is
so
it?
this is square root of 6, right? Yeah. Okay, that's good. Better?
Yeah.
Plus 6, right?
Mhm.
So it's not very clear what this is, right? What is the correct one? If I ask you, since you guys have done complex numbers here, then what is the correct one?
First one, I square.
The top one.
That we need to write I square 6.
Yeah, so then you would write I square 6, right? So this is I square, and that's the minus 6. And it is not the plus 6, but it cannot be. I mean, since we have a lot of correspondence with our Argand diagram, we are more confident about this, but Euler had struggled with this. So, and in fact, there are mistakes in Euler's work because of this. And again, it's okay to have mistakes, but it's just that Euler has made a
So
mistake.
this
We
second
pointed
one,
out.
we
So
cannot go through like that in second.
in Euler,
In second one, minus 6. I think we need to introduce imaginary. That minus 6 is doesn't exist at all.
this one.
Yeah. Or anything inside is square root negative.
Yeah, inside square root, but
We cannot-
square root of x
that.
times square root of y is square root of x times y, right? This is allowed, right? From here to there.
Mhm.
Or hoping that this is allowed, right? If this is also allowed and that is also allowed, then you say that why is this not allowed, right? Like then this is a confusion there as to which is the correct one. This doesn't seem to be wrong, right? At least put it like that. So if there are two answers, then how do you fix your answer? So, or if there are more than one answers, how do you? How do you?
That upper one is also plus 6.
Upper one is plus 6? No,
Minus
this is I, right?
Yeah.
I times I is
I.
minus 1,
Oh,
correct?
yeah, I got it.
Right?
Minus. Yeah.
Okay. So there is a homework problem I give based on this, just to clarify. And with argon, like in the diagram, and then that works out very well. And that's a confusion. So in fact, there is the multiplicity of those plus or minus is there, but we'll remove that confusion. That was a very broad introduction to complex numbers. Next time we'll define the derivative of a complex number.